Abhishek, why no one is joining?
Sir, I'm telling them in the group, sir. Just a second.
Okay. Good evening, all.
Good afternoon, sir.
Yesterday there was too much thundering and rainfall.
Yes, sir. Today also, sir. At, in the morning, sir, and in
Right.
the night also at land.
Yesterday night there was no power. Total power cut off was there. Hope that there will be no network issue because of this weather condition.
Yeah.
Okay, so last class about doubly reinforced beam. We have discussed the design steps, the working principle, and what are the advantages of doubly reinforced beam. Today I will discuss beam. I will show you, and then I will proceed for the flexural design. All of you have understood this concept of double it is and beam with reinforcement area suppose AST1 and another section B of compressive zone reinforcement and consecutive extra tensile reinforcement in the form of AST2. So this three different types of area of steel to be provided, and the combination will be a section, a doubly reinforced section. So I'm just recapitulating the yesterday's analysis double reinforced beam this slide because it would be necessary. And stress diagram we also know. We have also from stress diagram we have derived we have seen what would be the neutral axis, how to calculate it, and we have also seen the how to get the moment of resistance due to the presence of this doubly reinforced presence of this compression zone reinforcement. There will what will be the difference, what will be included. We have also seen the how to use the design aid, the table F of SP16, where we will get the d dash by d ratio, and using this we will find the value of FSC. So let me just uh, has been RCC beam and of cross section area 300 mm by. We have been asked to find out the point of resistance. Okay, the beam is reinforced with 4 number of 25 mm dia at the tension zone and 2 numbers of 20 mm dia is placed at the compression, and the distance is 50 mm from the top of the compression zone. Effective depth of the compression reinforcement from the top of the fiber is given, and M20 concrete and steel. So for this, we have to first find the area of the tensile reinforcement AST, that is AST1. We know the value of ASC. Okay, D dash is 50 mm, FCK is 20 Newton per mm square, Fy is Fe is 415 Newton per mm square. So all these values are known. So from here, we since d dash is given, so d dash by d ratio, that is 50 by 450. We will get and for the corresponding value of grade of steel, that is for Fe415. We have to check the which value of FSC is coming for the d dash consecutive d dash by d ratio. So here we see that the d dash by d ratio is coming 0.11. Okay, so we cannot take the value of 0.11. We have to actually take the value 0.10, that is 0.15. From the value of 0.15 for Fe415, from the table you can see it is how much? 342 Newton per mm square. So we have to consider FSC as 342 mm square. Okay, if this d dash by d value comes below 0.1, suppose it would have come as 0.8 or 0.08 or 0.07, then what would have we taken? We would have taken the value of 0.1. Okay, so once the range is within the given values, means 0.05 or 0.1 or 0.15 of d dash by d value, that value we have to take in, okay, minimum. And once the value exceeds of the given values here d dash by d, so we have to take the higher range. Okay, understood? So next is we have to what? Find the depth of neutral axis. We know that for the depth of neutral axis xu, the formula we know 0.87 Fy AST minus FSC into ASC by 0.3. So from here we will find the value of neutral axis. To check for xu max, we know the value of xu max. How to get it? Okay. From previous chapter we have already seen that for Fe415 ratio of xu max by d is how much? 0.48. So xu max we will get from here. Now we have to check whether it is a minimum or maximum respect to xu value of xu. So we see that value of xu is more than xu max. Okay, so we conclude that this section is over reinforced. Okay, so what we have to do, we have to find this moment of resistance considering value of xu max only. Okay, means 216 mm. Using this we have to design the for moment of resistance. So considering xu max to xu, that is 216 mm, we have to find the value of mu. And the value of mu, the equation you know, 0.6 is FCK B into xu max whole multiplied by d minus 0.4 to xu max plus FSC into ASC into multiplied by d minus d dash. Okay, all these equations have been derived in previous class. All of you know how it comes. So this is just a very simple example for carrying the design of doubly reinforced beam. Okay, so if the value of xu max would have been less than xu, then we would have taken the value of xu, and we could have proceed to find the value of mu, and so on. Next, let us see the reinforced beam for design of flexure. Okay, we know what is flexion bending. So for design of bending, we have uh, to make it resist the bending moment. We have to design considering the flexure. So the design for flexure, we have to consider the sufficient reinforcement that are provided to resist the flexure that are present in the tension zone. And since it is a doubly reinforced beam, so for compression zone also we have to consider. So for this, we have to maintain a particular reinforcement area in tension zone as well as in compression zone, and that area has to be restricted. Okay, so from previous drawing, the drawing of section that I've shown for AST1, so from there we can get the value for singly reinforced balanced section beam. The value of AST1 could be find out in terms of mu limit divided by 0.87 fy into d minus 0.42 xu max. Okay, it is same for single reinforced beam. So actually we will be dividing the reinforcement for we will take out in terms of singly reinforced beam and doubly reinforced beam. Okay, means AST1 and AST2. So for considering the next section, if you recognize, if you remember the two sections that I just shown in the starting of the class, one first section was comprising of singly reinforced beam AST1, and second section was comprising of compressive zone reinforcement, that is ASC, and as well as tension zone reinforcement AST2. So this value, to find the corresponding value of AST2, we have to take out in terms of section 2, and the corresponding moment for that is mu2, and here mu2 is actually the total mu value minus mu limit. Okay, we know that mu is equal to mu limit plus mu2, so mu2 is equal to mu minus mu limit. So subtracting the value of mu from mu limit, we'll get the value of mu2. So that is in terms of FSC into AC minus FCC into ASC multiplied by d minus d dash. Okay, we know what are these values: FCC and ASC. Okay, AC is the area of steel in compression zone, and Fs is the yield strength of steel, and CC is the value of uh, steel in the compression zone, and the area that is actually occupied by the steel in compression zone. So the concrete there will be subtracted. So that is why minus value is here, minus FCC into ASC into d minus d dash. D small d is the overall depth, we know, overall sorry, not overall depth, effective depth, and d dash is the effective clear cover, effective cover uh, of the compression zone reinforcement. So AST2 turns as mu2 by 0.87 fy into d minus d dash. So for both tension zone and compression zone, this value mu2 is applicable. So from here, the value of AST, the total area of steel, could be find out in terms of singly reinforced beam, and AST2 for the corresponding steel that is present in the section 2, that is for your doubly reinforced beam for So next is the corresponding value of area of compression zone enforcement. Okay, we already know mu2 is FSC into SC minus FCC into SC. So here, if we do not consider the loss in the concrete area, so neglecting that part, so mu2 turns as FSC into SC whole multiplied by d minus d dash. Okay, so the final value of ASC. Okay, so total area, that is area of steel that is required for the compression zone, is in terms of mu2 is mu2 divided by FSC into d minus d dash. Okay, so from all these values we can now give a brief about how the design has to be carried out step by step. So these are the design steps given here as followed. The dimension, if the dimension of the beam is given, the width and the overall depth, or the width of and the effective depth, the grade of concrete and steel will be given, and factored bending moment mu would be given. So from it should determine the value of FSC and from the ratio of d dash by d as seen in the previous example from table 1, means from table F of SP16 design it, we can get the value, corresponding value of FSC. Okay, and so d dash is what the effective depth of the compression zone reinforcement from the, so d dash should also be. Next is to determine the value of XU and check whether it is coming within the limits of XU max or not. XU max, as discussed, uh, the ratio of XU max by D is known for various grade of concrete. For mostly for Fe415 it is 0.48. So from there you will get the mu limit. Mu limit formula 0.66 FCK into B into D minus 0.42 XU max. Okay, so after finding out the value of XU max, you will find the value of mu limit. Okay, next step is to determine the AST1, that is area of steel for the section considering singly reinforced beam. So value of AST1 is mu limit divided by 0.87 Fy into D minus 0.42 XU max. Okay, we have already seen how this value is coming in the previous chapter. We have discussed how this value is coming for singly reinforced beam. Next is for mu2, that is for finding the value of AST2, that is the for doubly reinforced beam, means for compression zone reinforcement, the corresponding value of will be AST2. So we have to subtract the total factored moment with the limiting moment. So from here we get the value of AST2 as mu2 divided by 0.87 Fy into D minus D dash. Okay. If you are having any difficulty in understanding, you can say, you can interrupt me, and then I will again I can discuss the analysis of doubly reinforced part. total AST, that is AST1 plus AST2. So after that, we will choose a suitable diameter and we will right for the requisite spacing. We will distribute for minimum. Next step is to determine the, since all the tension zone reinforcement is has been found out. Now next step is to determine the compression zones reinforcement, that is ASC. So that ASC is actually mu2, that is the moment that is necessary for your compression zone reinforcement, that is mu2 divided by FSC into d minus d dash. So again, from here a suitable diameter of bar is chosen and it is provided for a particular spacing. Next is to check for deflection, for the control of deflection. It is similar to previous problem, the as discussed previously. For singly reinforced beam, we have to find the value of area of reinforcement in terms of PT, and from the table, from the plot that we have discussed for the factored value of tension, and we have to find the value of PT in terms of 100 AST by BD, and consecutive value of FS we have to find out, and from there Fs is known as 0.5 Fi into AST provided by AST required. As been already discussed in the previous chapter, it is similar. Find the deflection for L by D max, that is 20 into KT into KC for simply supported beam, and 7 into KT into KC for cantilever beam. And we have to check for L by D max and L by D provided. If L by D max is more than L by D provided, then it is fine, and if less, then we have to redesign for another section by considering another section. So once all the design steps have been considered, next is to redesign if required, and next is to check for the shear, and shear reinforcement is to be provided, and that has been discussed already. We have to check the value of tau v, tau c, and we have to provide the shear reinforcement as required. The formula is same and the procedure is also same. And finally, we have to check for the development length as per the codal provision, as given here is m1 by vu plus L0 should be more than LD. And the final step is to design the sketch the various reinforcement and final cross section that we have considered, that is designed. So we have to draw the L section and cross section of the beam that we have obtained after designing. Okay, next step is to use of the design aid. So the use of this design aid to find the value of compression zone reinforcement is to be discussed. Okay, so from this design chart and the table, as you can see, doubly reinforced beam are designed, and from here we can actually see for different grade of steel, and for a multiplying factor, that is AST2, we will get the factor for ASC, that is in terms of d dash by d. Okay, so this actually is obtained by the plot against d minus d dash. Okay, for the value of mu2, for consecutive value of your grade of steel. So this table is actually obtained from the design curve. Okay, and for the different value of d and d dash, for your that is obtained from the design aid chart 19 and 20. Okay, from there, and here we see that the for the doubly reinforced beam, the moment, the ultimate moment, that is mu, is equal to mu limit plus transverse. So if you put the values of ms32, T2, that is mu2, it is 0.87 FIST2 into d minus d dash. So mu is equal to mu limit plus value of mu2. Now you also know that mu by bd square, if you divide it by bd square, then you will obtain mu limit by bd square plus, instead of writing ast2 by bd into 100, we can write as pt2 by 100 into 0.87 fy into 1 minus d dash by d. Okay, since we know that pt2 is equal to ast2 by bd into 100, and where this pt is the total area of steel, and that is given in terms of pt limit plus pt2. Okay, for consecutive value of mu limit and mu2. So from here, from using this percentage of steel in the compression zone, we can write value of ASC is equal to mu2 by FSC minus FCC into d minus d dash. So putting this value of mu2, we can obtain the value of PC, that is in terms of PT2 into 0.87 Fy by FSC minus FCC. Okay, I hope no problem for FSC is what? FSC is the stress in the compression steel. Okay, and FCC is what? Is the stress in concrete at the level of steel. So since the stress in concrete at this level of steel is neglected, since it is occupied by the, so only FSC is acting stress in the compression steel. So that is why FSC minus FCC. Okay, and from the design aid table 50, we actually get this consecutive value of mu by bd square for getting the value of pt and pc for consecutive d dash by d ratio. Okay, so the complete table is not shown here. Only half partial section is shown here because of the non-availability of space. So you can download the SP16 if you have, if you don't have, and otherwise, and from here we will actually get the value of particular PT and PC for the consecutive d dash by d ratio. So let us discuss a design example for the flexure, for the design of flexure of doubly reinforced beam. So a RC of size 230 mm by 500 mm, and it is subjected to factored movement of 200 kN meter. So we have been asked to find the reinforcement that is should be required for the grade of concrete M20 and considering Fe415 steel. Okay, so given values are the width and depth. Uh, the factored moment is given, mu value is given, FCK Fy is given. So first we have to calculate the value of FSC. Okay, so FSC can be obtained by the T dash by D ratio. So from the table for grade of concrete Fe415, since the ratio of D dash by D is coming 0.1, so we can use this value for Fe415 D dash for D dash by D value 0.1 from the table of the from the table F of design aid, that is 353 Newton per mm square. Next step is to find the limiting moment of resistance, mu limit. So this mu limit is actually in terms of the singly reinforced beam section. So it is the usual formula 0.36 FCK B into Xe max into D minus 0.42 Xe max, and the value of Xu is also obtained for 0.48 D in terms of balanced section. So from here we will get the value of mu limit, and mu2 we know it is mu minus mu limit. So from the consecutive value of mu we can find out the value of mu2. Okay, all of you have understood. Next step is to find the area of tensile steel. Area of tensile steel AST is equal to AST1 plus AST2. Okay, the value of AST1 is actually in terms of singly reinforced beam section 1, that is mu limit. So the usual formula is mu limit by 0.87 Fy into D minus 0.42 Xe max. So we can find the value of AST1 like this, and AST2 we know is for the section 2, means for compression zone reinforcement section. So AST2 is the compression zone, this is the tension zone reinforcement for the compression zone reinforcement section. For double reinforced beam, that is in terms of mu2, so that it will be mu2 by 0.87 Fy into D minus D dash. Okay, so from here AST2 is obtained. So total area is AST1 plus AST2. So we obtained the total area of steel, and by considering suitable size of reinforcement, total
Sir,
number of reinforcement.
sir, why we are taking 20 bar, sir? Why not? How will, sir? How we will check this that we have to take 20 bar or 25 bar or 16 bar, sir?
नहीं नहीं, उसका कोई चेक नहीं है. That is up to you. We can take 20 bar, we can take 25 bar, we can take 16 bar, but in general we have to make sure that for a particular beam there should be at least 2 number of bars and at most 4 numbers of bar or 6 number of bar, not more than that.
That
Okay,
we can
so
calculate, sir. But my question is that for any sir, like we are designing a random beam, sir. For that, how much of bar we can take, sir?
as per codal provision, for beam, for column it is minimum 12 bar per column,
Okay, sir.
and 12 or 16.
तो मतलब हम रैंडम के लिए उसका मिनिमम लेंगे तो कोडल प्रोविजन के हिसाब से.
हाँ,
नहीं हाँ मिनिमम तो लोगे सपोज इन जनरल सपोज 16 mm or 20 mm bars are used okay for a suppose smaller section of beam suppose 150 mm का width हो गया या 200 mm width हो गया और 300 mm depth हो गया स्मॉलर सेक्शन या फिर 150 mm width हो गया और 250 mm का डेप्थ हो गया इस टाइप का सेक्शन जो होगा उसमें 16 mm का डाया दोगे तो हो जाएगा लेकिन when you are considering higher section suppose 300 mm by 400 mm then obviously will require larger dia 20 mm or 25 mm okay so
Yes.
even if you suppose you provide instead of 20 mm if you provide 25 mm okay so that would not be wrong
सर
अगर
बट
25
कॉस्टिंग तो इंक्रीज कर रहा है ना सर
नहीं 25 दोगे तो क्या होगा नंबर ऑफ बार्स कम हो जाएगा
अच्छा
if you when you have considered 20 mm bar number of bars is coming 4.3 suppose 5
yes
okay so अगर तुम 25 mm का कंसिडर करके देखो उसको डिवाइड करो अभी you take out calculator and do it now see how many bars are coming 1354 divided by pi by 4 into 25 square करो कितना आ रहा है देखो
सर तो कितना 25 mm बार
25 mm बार के लिए देखो कितना नंबर ऑफ बार्स आएगा एरिया तो सेम रहेगा ना
यस सर इसका एक मिनट सर
pi by 4 into d square कितना आ रहा है वैल्यू
एक मिनट सर कर द 490.87
491 पकड़ लो so 491 ज्यादा आ रहा है
प्रॉक 53 सर तीन
यार
बार
3 दे सकते हो तो ठीक ही है मतलब 2 साइड में रहेगा और एक बीच में रहेगा so when you are providing 25 समझ में अगर तुमने एग्जाम में 25 करके भी किए तो वो गलत नहीं है इट इज राइट लेकिन जब तुम 16 mm लोगे सपोज इंस्टेड ऑफ 20 mm you took 16 mm तो क्या होगा बोलो अगर 16 mm पकड़ के
तो बार इंक्रीज कर देगा नंबर ऑफ बार विल बी इंक्रीजिंग
हाँ,
सपोज
तो
6 या 7 हमको लेना होगा
हाँ सपोज 7 8 लेना होगा तो इज इट डिजायरेबल 8 नंबर ऑफ बार्स
नो सर नॉट डिजायरेबल एक्चुअली क्योंकि एक पतला सा सेक्शन के लिए इतना सारा बार दे देंगे तो एरिया ऑफ बार ज्यादा हो जाएगा
नहीं एरिया इज कांस्टेंट एरिया तो कांस्टेंट है नंबर ऑफ बार देने से क्या प्रॉब्लम होगा ज्यादा बढ़ा देंगे तो
टेंसर
sufficient space no sufficient space for concreting मतलब कंक्रीट को तो अंदर जाना पड़ेगा ना सेक्शन बीम के अंदर ऊपर से जब तुम पोरिंग करोगे तो सफिशिएंट स्पेस होना चाहिए ताकि मेरा यूनिफॉर्मली कंक्रीट बीम के अंदर तक जाए कास्टिंग के समय में बोल रहा हूँ कास्टिंग के टाइम में
यस सर
अगर रिइंफोर्समेंट रहेगा तो क्लमजी so this 20 mm bar or 25 mm bar is the perfect number that we can use कभी कभी प्रैक्टिकल पर्पस में तुम देखोगे साइट में कभी कभी एज पर डिजाइन सपोज दिया है 25 mm बार सो लेकिन साइट में समझो 25 mm बार अवेलेबल नहीं है 20 mm बार ही अवेलेबल है सो बीइंग ए साइट इंजीनियर इट इज योर ड्यूटी टू कन्वर्ट दिस keeping the area constant convert this number of bar in terms of your size specification ठीक है तो जैसे अभी किया तुमने 25 mm बार के लिए तो वैसे ही एक्चुअली प्राइवेट साइट में भी डिजाइन प्रैक्टिकल मतलब प्रैक्टिकल साइट कंस्ट्रक्शन में भी ऐसा ही होता है अगर कोई बार अवेलेबल किया जाता है इसी तरह से, keeping the value of the area constant. Okay, next, moving to the next part, that is so till now we have discussed the tension zone enforcement. Okay, AST1, AST2, I hope सबको समझ में आया AST1 क्या है, AST2 क्या है. Next is ASC, that is compression zone enforcement, and उसका जो है formula वो है mu2 in terms of mu2 by FSC into d minus d dash. So from here we will get the value of ASC, and similarly see here, since the area is lesser, so we can use 16 mm dia bar. So like this way the design is done.
यहीं तक रहने दीजिए सर आज.
अच्छा ठीक है, ठीक है, यहीं तक रखने देते हैं अभी. So the next step